now we are looking at Chapter 3, Section 5, and it's called Projectile Motion. And projectile motion is when an object is going to travel through two-dimensional space, and the only reason why it's changing its direction is because it is under the influence of gravity, Earth's gravitational pull. So, with projectile motion, as you see in back of me, there could be an object, could be anything like a soccer ball, a football, a golf ball, a projectile. Something is being launched into the air, and it's being launched into the air vertically, but with some initial horizontal motion. So it's being launched up and horizontally. And if it does that, then we would say that that object is a projectile. If it's not accelerating itself, once it leaves the object that's launching it. If it's a football, once it leaves the foot. If it's a bullet, once it leaves the gun. If it's a golf ball, once it leaves the club. Whatever's launched it, once it leaves, then it is going to be traveling through the air in two-dimensional space. It'll follow a parabolic path, and we call that projectile motion. It'll be moving in two directions at once, and the way we're going to try to solve this is we're going to try to analyze it using two directions in two different times. We're going to break up this problem into two different one-directional motion problems. Okay? So in a lot of this section, we deal with tangent lines to curves. So when this ball is originally kicked off the ground or thrown or launched, whatever, the ball here is moving with a certain speed. And so we would say at this particular moment, it's launched with a certain speed. I'll try to draw a line that's tangent to this part of the curve. It's launched like this. Okay, it's a little bit steeper than the real path would be. That's its launch point. The moment it was launched, it was moving with a little bit of horizontal velocity and vertical velocity. So if I break this thing down into the base components, see there was some launch angle, and then this would be the true initial velocity. But this one here would be the initial velocity in the x direction. And this one right here would be the initial velocity in the y direction. Okay? And later you can see, as the ball is moving all the time later, this would be its true velocity, but it's moving with some horizontal speed and some vertical speed. And later over here, if I draw kind of to the tangent of that curve, it's moving like this. That's its velocity. It's not anymore the initial, but it's moving with some horizontal and some vertical. And when I get up here, if I try to draw that, it's moving basically like that. That's its velocity. It's got no vertical piece to it. It's all just horizontal. So the way we analyze this is we look at the horizontal pieces and we look at the vertical pieces and we keep them all separate. And when we deal with this two-dimensional motion called projectile motion, we can answer questions like, if this was a football, we could say, how much time is this football going to be in the air? We could say, how far downfield is it going to be landing so the players can be in that right area? We could say, what's its velocity going to be at any moment along the path? You know, with the military, ancient days, they would have cannons, and they would fire a cannon at a cannonball at a castle. We could say, how far away is this cannonball going to be hitting a certain point? If it hits the castle halfway up here, we could say, how fast is it moving at this particular point? How many seconds does it take to get to this particular point? So all of these things can be figured out with formulas, and we're going to be working in two dimensions here. When I say projectile motion, what we talk about is we say projectile motion is basically free fall with an initial horizontal component to the velocity, the initial velocity. So the way we're going to do these problems is we're going to keep all of the x components and all of the y components separate. So if we keep all of the x components and the y components separate, what we're going to do is we're basically going to be focusing on a one-dimensional problem. So when we talk about in the x direction, it's going to be going at a constant velocity. So in the x direction, we'll be talking about a constant velocity. And we'll only use one equation. This will be the only equation we're going to use. In the x direction, we're going to say it's a constant velocity, and we'll say delta x is equal to vx times t. And that's the only thing we're going to be doing. Vx will be the velocity in the x direction, which will never change. This velocity in the x direction will be the constant. Okay. In the y direction, we're going to be using those things called the free fall formulas. So with the free fall formulas, there were 4 formulas of constant acceleration, and that's what we'll be using when we're talking in the y direction. So we're going to keep everything separate. We're going to break everything down into its x and y component pieces. So this particular problem says there is a ball, and it's going to be rolled off of a table at 5 meters per second. It says the table is 1 meter tall. It says find how far from the base of the table the ball will hit the floor. So what's going on is we have a ball that's rolling. So it's rolling this way. It's rolling along a horizontal table at a speed of 5 meters per second. And when it gets off the edge of the table, it is going to go, and it is going to roll with a parabolic path. So it's going to be going through this path. Okay. So you see, here, when the ball is here, it's simply moving at a speed of 5 meters per second. That's our initial speed. And how do we go about doing this? Well, you see, what's happening is the ball is moving with a parabolic path here. So every time it goes over a little bit, it's moving down a little bit. So it keeps on going over and down. And what I've tried to do here is I've tried to draw some, almost they look like steps. I've tried to make the horizontal piece the same each moment. So the horizontal piece is always the same. And you notice how the vertical piece is getting a little bit bigger, bigger, and it's very big. So this isn't to scale or anything, but what I'm trying to show is there's going to be a constant velocity in the x direction, and the velocity in the y direction is constantly changing. In this case, it's constantly getting bigger. So if I broke all of these things down into an x and the y component, I could make like a table. In the x direction, we're talking about constant velocity. So the only things I'm going to need are delta x, v in the x direction, and t. In the y direction, we'll be talking about free fall. And the only things I'm going to be needing there will be everything with free fall. Delta y, v initial in the y direction, v final in the y direction, a in the y direction, and t. This is a template right here. You could make this template in your notes, and every time we have a projectile motion problem, you could write this template and then plug it in based on what they're talking about in the word problem. So as far as this word problem goes, if the ball is rolling along a table, the table is meant to be horizontal. So if the ball is rolling along a horizontal table at 5, when it becomes airborne, its initial speed would be 5. So this is 5 meters per second. Okay? Sorry. The initial speed of it is 5 meters per second. Okay. In the x direction. Now, if it's only going horizontally when it's rolled off the table, then it's not moving vertically. So that means the initial velocity in the y direction is going to be, the initial velocity in the y direction will be 0. See, this is the most tricky part right here. If you have a ball that's rolled horizontally, all of its speed is going in the horizontal direction. None of it's going in the vertical. So this piece here is 0. Delta x, that's what they want to know. How far from the base of the table? So what's happening is, this is the base of the table. They want to know how far over is it going to go. That's delta x. So that's what we're looking for. Delta y, they told us this table was 1 meter tall. So you see, we're going to start up here, and we're going to end on the ground. So we're going to be going down. So the table is 1 meter tall. Delta y is going to be negative 1 meter. We're going to be falling downward. Final velocity, I don't know. I have no idea what the final velocity might be. The acceleration due to gravity, I do know. It's negative 9.8. Okay. And the time, I don't know. So the way these type of problems work is, we're working independently. We're keeping our x components completely separate from our y components. And the way they're connected is the time. The amount of time this ball is moving horizontally through the air is exactly the same amount of time that the ball is moving vertically through the air. So if I can find the time on one side, it's the same time on the other side. Now, which side should I use? Well, if you look at what we've given, I have 3 things over here in the y column, and I only have 1 thing over in the x column. So I'm going to start working in the y column. And I'm going to say this. We'll work vertically first. So if I'm working vertically first, I'm going to just basically find a formula that'll help me find the time. So the formula that I can think of would be this. Delta y equals v initial y t plus 1/2 a y t squared. Notice how I'm being very careful with my subscripts on subscripts. This is not just the initial velocity. This is the initial velocity in the y direction. This is not just the acceleration. It's the acceleration in the y direction. And I don't really have to do it, but I'm just doing it to teach you. We're talking only about one component, the vertical direction. So I don't want you to think the initial velocity is 5 meters per second in the y direction. Okay, so over here when I'm talking about work vertically, you have to only make sure you're getting the y pieces, the vertical pieces. Okay. So what is delta y? Well, I'm looking at this column. Delta y is negative 1. So it's negative 1 meter equals, what's the initial in the y direction? 0. Time is unknown. Anything times 0 cancels out. Plus 1/2 negative 9.8 times time squared. So this becomes negative 1 meter equals, this is negative 4.9 meters per second squared, and this is times time squared. And I'll divide both sides, so it's going to be negative 1 meter divided by negative 4.9 meters per second squared equals t squared. T is going to come out to be a number. I have to just do it on my calculator. Well, first of all, let me say t squared came out to be the number 0.204. 0.204 seconds squared. So if I hit the square root button, t is going to come out to be 0.45. So once I square root both sides, t is equal to 0.452. So that's the time. So I can put the time right here. So the time is 0.452 seconds. And the time is also going to go over here. 0.452 seconds. This is the critical part. These are the same. Since I know the time on one side, I know the time on the other side because they're the same. And now there's only one thing missing from the horizontal side. And that is what delta x is. So I can calculate delta x. So if I work horizontally, there's only one formula that I know of when we talk about a constant velocity. That formula would be delta x equals v initial in the x direction times the time. Okay, that's it. So I do know what v initial is. V initial in the x direction is 5 meters per second. And we just figured out the time was 0.452 seconds. So if I multiply those, so it comes out to be 2.26 meters. And that's telling us how far the ball will land from the base of the table. 2.26 meters. How about if I added a part 2 to this and I said, find the final velocity? So if I said this was A, I could say B. Find the final velocity. Meaning, what's the velocity of the ball right at the moment when it's about to hit the ground? Not after it hits the ground, but when it's about to hit the ground. So this is a tricky question, and a lot of students would be tricked by this if you didn't think about it, but think about it a little bit. A lot of students might go and just say, let me find this, let me find this. Well, is this the final velocity of the ball? And the answer is no. This is the final velocity in the y direction. Okay? Nobody wants to know what the final vertical velocity is of a ball. If a ball hits you in the head, what you want to know is how fast was that particular ball going, not what is the final vertical velocity of the ball. So a lot of people would just find this and stop, and you're halfway there. But when the ball lands, if you can kind of see up here, the ball's moving in two directions when it's about to hit the ground. The ball's moving horizontally and vertically right when it's about to hit the ground. So we need to use both components to find the real final velocity. Okay. So we do need this piece first. So I'm going to say this. I'm going to say work vertically first. So I'll use a formula. I have everything else here, so I'll use the simplest formula for me. V final in the y direction equals V initial in the y direction plus A in the y direction t. So again, I'm being overly cautious by saying I'm going to work vertically, and then I'm also putting a subscript on a subscript showing you that I'm definitely working vertically. So the final velocity is unknown. The initial velocity is 0 in the y direction. The acceleration in the y direction is negative 9.8. And the time we calculated is 0.452. So V final y, I have to calculate that. It equals a negative 0.43. Sorry, a negative 4.43. So what I've just found is the velocity in the y direction right when it's hitting the ground. So this is a negative 4.43. Okay. How would I figure out the total velocity when it's about to hit the ground? Let me zoom into it. If I zoom into it, what's happening is right before it hits the ground, it's moving. This is not a good scale. It's moving in two directions. In the x direction, it is moving at 5 meters per second. And in the y direction, it's moving with a speed of negative 4.43 meters per second. So the real ball is kind of coming, it's going through the air, and it's kind of coming like this. Okay. This right here is the true speed of the ball. We're trying to find this piece. When it's about to land, we were told it has these components. So it has a 5 to the right and a 4.43 going down. As you can see, what I'm trying to draw on the board here comes out to be a triangle. The base of the triangle, the horizontal piece is 5, and the vertical piece is 4.43. I didn't have to put the negative because the arrowhead shows the negative. So how would I get this piece you get the magnitude of any vector by saying the square root of the base, 5 meters per second squared, plus this squared. Okay, so the magnitude equals, well, I just have to do that math on my calculator. The answer comes out to be 6.68. So this true speed of the ball here is moving with the speed of 6.68 meters per second. And it's about to crash into the ground. It's moving to the right and down. So when they say velocity, we're talking about a vector. Every vector has two things. A magnitude. I've found the magnitude. But it also has a direction. So how would I get a direction? I need an angle here. So the angle here, I would use this formula. Tangent minus 1 of the y piece. So v in the y direction divided by the x piece. Okay, so it's going to be v in the y direction final divided by v in the x directional final. So this would be tangent minus 1 of these numbers, 4.43 divided by 5. And that's going to be 41.54 degrees, and it's going below the horizontal. Those two things are going to tell us how the ball is moving right when it hits the ground. It's moving with a speed of 6.68 meters per second and at an angle of 41.54 below the horizontal. Okay. So if I just clean that up one more time. So the ball is falling. So what happens is this. Here's the ground. And the ball was coming through the air and was about to hit the ground. So the ball hit the ground right here. So at that particular moment, it was going, as I said, and it had some x piece and some y piece, and this was 5 meters per second, and this was 4.43 meters per second, and this is the angle I'm talking about of 41.5 degrees below the horizontal. If it broke through the ground, it would break through like this, and that would be below the horizontal too, 41.5 degrees. So the drawing up here is not perfect to scale. It's not terrible, but it's not the best. So that's how to do this particular type of problem, where they ask you to work with two dimensions simultaneously. So what we did is we separated everything into one dimension. So we focused on the x direction, what's happening here, and we focused on free fall formulas, what's happening here. Here's a problem dealing with projectile motion. It says this: Napoleon's cannons had muzzle velocities of 60 meters per second. So all of his cannons had a speed of 60 meters per second. I don't know how reliable this information is. I'm saying if we fire that cannon 35 degrees above the horizontal across a flat field, what's the total time that cannonball is going to be in the air? And I'm pretending now that it's going to land and end at the same elevation. Okay, so that's not overly practical, but let's just pretend it's landing at the same elevation. So here I have a picture of it. So this is just the moment. It'll never follow any straight line. Don't try to do triangles here altogether, because the ball's never going to follow a straight line. This is the moment when it's launched. So there's a cannonball here. It's going to be launched. And it's going to go through the air, and it's going to go in a parabolic path, and it's going to land on the ground. So at the moment of launch, we're told it's going with a speed of 60 meters per second and an angle of 35 degrees. We can never work with vectors going in two directions. So we need to break this apart into the x and the y piece. So we need to figure out how fast is it going, what's the initial speed in the x direction, what's the initial speed in the y direction. So we need to use our sine and cosine functions to do that. So we learned about that already earlier in chapter 3. So if we break this vector down, and make sure your calculators are in degrees, what we get is this. In the x direction, remember to do this, we would basically say it has to come out to be a number. So Vx is going to be the hypotenuse times the cosine of the angle. So if you plug that into your calculator, it's going to come out to be 49.45. Wait a minute, 49.15. And if you do the y piece, remember the y piece is just a formula. You're going to take the hypotenuse and you're going to multiply it by the sine of the angle and make sure your calculator is in degrees. And if you do that correctly, you should get 34.41. So this is going to be 34.41. Okay. Now that's its x and its y directional velocity. So when it's launched, it's going horizontally with a speed of 49.15 and vertically with a speed of 34.41 meters per second. And it's going to go through the air. When it gets up here to its maximum speed, it's only moving horizontally. So when it gets up here at the maximum speed, it'll have a velocity in the x direction of the same, 49.15. And in the y direction, it'll be going at 0. Because when it gets to its maximum height, it stops going up, and it hasn't yet started to go down. So its speed at its maximum height is 0. In the y direction only, not the whole thing. And since we can use symmetry whenever we can use symmetry, if we go across this whole thing here, when we get to the final point, it'll land very, very symmetrically to the way it took off. So it should be landing at a 35-degree angle again, and it should be coming in at a total speed of 60 meters per second. So you see, as it's landing, it's coming down at 34.41 meters per second, and it's going horizontally at 49.15 meters per second. So we've picked a few different points to look at, and usually these type of questions, they can ask many things. Typically, the type of questions they could ask in this type of problem would be, what is the total time it's in the air for? And that's what this question another type of typical question you could ask is, how far would the range be? Range is a technical name in these projectile motion problems. Range means delta x. So they could say, how far is the cannonball going to be displaced in the x direction? So basically, where's the cannonball going to hit? Down here. How far is the cannonball going to travel horizontally and hit some place on the field? Another thing they might ask is, how high will that cannonball hit? What's the maximum height that that cannonball can ever hit? So all of these things are questions that are typical type of questions. So to answer this, we have to just use the x and the y components. So what I would like to do is I'd like to erase the question off the top of it and just keep the picture and then show you how to use some formulas. And I've still left the question. What is the total time in the air? Total time the cannonball is going to be in the air. So I recommend that we work in the x and the y components only. So here's the x component, and here's the y. And in the x direction, we have delta x. We have v in the x direction, we have t. And in the y direction, we have delta y. We have v initial in the y direction. We have v final in the y direction. We have a in the y direction. We have t. So those things there are going to be like a template. You can use this table for all of our projectile motion problems. You just have to be careful of where you want to say everything begins and everything ends. So where does everything begin? Well, obviously everything begins here. That's our starting point, definitely. Depending on the question, our ending point could be here, or our ending point could be here. For instance, if they said, how high does the cannonball fly in the air? What's the maximum height? I'd have to put my end here. And if I put my end here, it's not going to be the total time it's going through the air. It's going to be half of that. So, to answer this question, what is the total time the cannonball is going to be in the air? Well, I do need to put the word end right over here. Okay. So what I'm going to do is I'm going to use my components. So what is my velocity in the x direction as far as components go? Well, it's not 60 meters per second. 60 meters per second is the total, the real true speed. I only want the x component. So I want this one, 49.15. What is the initial y velocity in the y direction? Well, it says it right here, 34.41. What's my displacement? How far has this cannonball been displaced in the y direction? Well, it's a little tiny bit tricky. If you can see on this side, it's on the ground. So it's on the ground here, and if you go to the other side, it's on the ground. So if it started on the ground and it ends up on the ground, and originally I had written for you this problem, it's a flat field, that means it's not displaced at all in the y direction. So this is 0. It starts on the ground, it goes across a flat field, and it ends on the ground. What's my final velocity in the y direction? Well, it's in the picture. If we're using symmetry, what goes up must come down, and it's going to come down the exact same way. So the final velocity is right here. The arrowhead pointing down is telling me that this is a negative number. So it's going to be negative 34.141 meters per second. What's my acceleration in the y direction? Negative 9.8. Okay. So the question is, what is the time, the total time that the cannonball is moving through the air? Then we can get that by just solving for this time right here. So if I have these four things, I can use any one of the equations I want and find it, but I'm going to work vertically, and I'm just going to use one equation. So I'm going to do this. I'm going to say work vertically. And I'm going to say V final in the y direction equals V initial in the y direction plus A times t. And V final in the y direction is negative 34.41 equals positive 34.41 plus a negative 9.8, and the t is unknown. So again, now I'm just going to erase this problem here, this question a little bit. So if I subtract both sides with 34, on this side, I'll subtract 34 from both sides. It'll become negative 68.82 meters per second equals negative 9.8 meters over second squared times time. And I want to get the time by itself, so I'll divide both sides by negative 9.8 meters per second squared. So t will come out to be negative 68.82 meters per second divided by negative 9.8 meters per second squared, and that will equal .02 seconds. So there's a cannonball being shot by Napoleon, and the cannonball, we were told, was leaving at a speed of 60 meters per second and an angle of 35 degrees above the horizontal. We just figured out that it'll be in the air for 7.02 seconds. And I'm going to put that on both sides. Okay. So that's how to do that particular type. But like I said, there's usually 2 or 3 or 4 questions you can ask for this particular type of a problem. They usually ask some more things. The most typical question is, how far is the range? The range would be the distance from the starting to the ending point. So this thing right here, it's called the range. But it's a fancy way of saying delta x. So delta x is this thing called the range. So what would the range be if I launched a cannonball from this side, how far along the ground horizontally would it hit the ground right here? Okay. Well, to find the range, I'm looking for delta x. So delta x is right here. It's an x. Doesn't look like an x. That's an x. So we have to fix that. We have to work in the x direction, and we have to come up with some components. So I will erase this. I will say now work horizontally. So if we're working horizontally, then there's only one formula that have these three things in there, because this is a constant velocity. So it's going to be delta x equals v in the x direction times t. So we're talking about a constant velocity. A constant velocity formula, I should say. So constant velocity formula means there's no acceleration. We're not speeding up, we're not slowing down, we're going at a constant horizontal velocity. So if I plug that in, what we get is the velocity in the x direction is 49.15. The velocity in the, the time it's moving through the air is 7.02 seconds. If I multiply those, I get 345, basically. It says 0.03 meters. So this cannonball is traveling 345 meters through the air before it crashes into the ground. Okay, and I mean, I try to evaluate these things. Is it reasonable to me? Well, I know if somebody throws a football across a field, it's usually, 3 or 4 seconds. I don't really have experience with people launching cannons across a field, but I'm assuming it's going to be up in the air longer, so I can't really say if I feel this is good or not. I would actually, if I had to think, I would say that I think the cannonball should be up in the air longer than that. That's just my intuitive feeling. Is this a fair number? Well, I know a football field is approximately 100 meters across, so I would say this is about 3.5 football field lengths, and I would say, yeah, that is a good distance. So I think a cannon could be firing at something approximately 300 or 400 meters away. So I'm thinking that's good. I like that number. The other question they could ask is, how high does this ball go, cannonball go? So what's the maximum height? So if they were to ask you that question, everything on the board changes. Okay, so why do I say everything changes? Because if they were to ask that question, we would have to end here. Okay, and in the last question, we were ending here. We have the word here, end. But if it ends here, then we're going to take away half of this problem. So it's going to go away. I'm going to lose that too. See? So if we end here, a lot of things are changing. And when I say a lot of things, I don't know if you know what I mean by a lot of things, but what changes? Well, let's look at them one by one in the y direction first. What's delta y? If we're talking about ending up here, delta y is no longer 0. We've started on the ground, and we've ended up higher. So if they did say to find the maximum height, we wouldn't say that it's 0. That's what we're looking for. So this is changing. So I'll just cross that out. This is now an unknown. The initial velocity in the y direction is still the same. Nothing changed over here. So we were launching the cannonball the same way both times. So this is what's changing, the end pieces. So V final, before V final was symmetrical to V initial. It was equal and opposite because it was back on the ground. Now, V final is going to be now up in the air at the maximum height. It stopped going up, and it's just about to start coming down. So we would say, not this, but we would say it's 0 meters per second. Oops, that's the wrong one. So I'm trying to say the correct one. 0 meters per second here. So we would have to cross this thing out and say it's 0 meters per second. We would still say the acceleration is 9.8, negative because it's going downward. What about the total time it's moving through the air? Well, if we're stopping halfway, because it's symmetrical, at the top it's halfway, we have to take half of this time. So what would I do to get half of that time? I would divide it by 2. So 7.02 divided by 2, 3.51. So if I could just erase that, and you see, it comes out to be the time is 3.51 seconds. And this changes too. And all of this stuff over here is changing. But I don't even care about those things, because I want to know what's the maximum height. So I only want to work vertically. Okay? So if I'm going to be working vertically, then I have this, I have this, I have this, I have this. The only thing I don't know is delta y. I can use any formula at all for delta y with these 4 givens, and it should tell me what is my delta y, maximum height. So I could use this formula if I wished. If I plugged it in, I'd get this. I'm getting 60.39 almost. So this cannon is being shot across a field, and right now I've just calculated delta y when we're talking about here. So what I'm doing is I'm calculating the maximum height, and I've calculated the maximum height as being 60.39 meters tall. And I use this formula right here to do it, and that's a fine formula. I could have used other formulas if I wanted to. I could have said this. I could have said delta y equals v initial in the y direction t plus 1/2 a in the y direction t squared. That could have given me the exact same formula there. If I wanted to, I could have used this. V final in the y direction squared equals v initial in the y direction I could have said v final in the y direction squared equals v initial in the y direction squared plus 2 times a times delta y. And if I chose to use that formula here, I would get the, I'm sure, I'm not doing it, but I'm confident in physics, and I'm confident that physics works, so it should give me the exact same answer right here. Okay? So that's how to do a problem like this, where we have two-dimensional motion, we have to break up the components in their x and y pieces, and we solve the problem by using two different one-dimensional cases. So we looked at the horizontal case by itself, and we looked at the vertical case by itself.